So a special case where we're going to use our kinematic equations is when we look at projectile motion. When you throw an object, what factors influence how the object moves after you let it go? This is basically thinking about, well, what forces do we need to include in the free body diagram for our object? Obviously, we need to include gravity, right? Anything you throw, it's got mass, gravitational force acts on it. You might also say, well, anything moving through the air, there's going to be some air resistance, some drag. Though this is certainly true for the vast majority of things that act like projectiles, you don't need to worry about the drag force. It is very small relative to gravity, and so therefore can effectively be ignored. So we're not going to worry about a drag force in terms of setting up our projectile motion problems. Again, you can, it just makes for a much more complicated problem. Well, what about the applied force as it's thrown? And again, here the key idea is after you let it go. So the object, while it's still in your hand, yes, you're exerting some force to launch it, but while that launching force is acting on it, it's not a projectile yet. So we don't want to think about any applied force acting on a projectile. What about a normal force from the surface when it lands? Once it starts to come in contact with whatever surface it's going to land on, your object is no longer a projectile. So a projectile is only a projectile and only undergoing projectile motion between the instances where it is released and just before it hits whatever surface it's going to come in contact with at the end. We don't have to worry about the normal force, which basically means that the only force acting on a projectile, at least in terms of the way that we're going to model this, is just the gravitational force. So if the only force acting on a projectile is the gravitational force, that means that the acceleration on a projectile has to be equal to gravitational acceleration. We know gravitational acceleration always points downward. So if you have some object that's acting as a projectile, so it's following some parabolic flight path, and at any particular instant you pick, it's traveling at in a velocity that's tangent to the curve that it's traveling along, its acceleration points straight down. We've learned, hopefully at this point, that there's some utility in terms of lining up coordinate systems with the acceleration, and this is no different. It simply means that when we have projectiles and we're working projectile motion problems, we want to make sure that we use a coordinate system that lets x be horizontal and y be vertical, which means that we can break up the acceleration vectors into its two components, and we know the x component will always be 0 given this choice of coordinate system, and the y component can be either positive or negative depending on whether you let up be the positive y direction or down be the positive y direction, but the entire magnitude of little g is going to be in that y component. And so you're going to have g equals 9.8 meters per second squared, and whether that's positive or negative is going to depend on whether you let positive y point up or positive y point down. And so when you think about what these two components are trying to tell you, well, they say two things. One is that you know you have constant velocity motion in x. The horizontal motion of your projectile is constant velocity motion, and you have constant acceleration motion in y. With our projectile motion problems, if we just have vertical motion, so you drop something, you throw it straight up, we're just going to have the constant acceleration in y. But if you launch something so that it's traveling not just up and down but also horizontally, then you're going to have both constant velocity motion in x and constant acceleration motion in y. So let's look at a couple examples. So for starters, let's just drop something off the roof of a building. And so again, when I let it go, its initial velocity is going to be 0. As it falls, it's going to speed up. So it's falling down, it's traveling faster as it falls. The object speed increases as it falls, tells me that the velocity and acceleration must point in the same direction on the way down. That makes sense because I know the acceleration points downward. If I throw something up, so again, now stand at ground level and launch something straight upwards. Well, again, it's going to travel upwards, but slow as it does it until it reaches some highest point where again it's going to come to a stop. The object speed is decreasing as it rises, and of course that's because the acceleration still points down, and so the velocity and the acceleration vectors point in opposite directions as my object is traveling on its way up. Now, it's easy to forget, but it's the velocity that's zero at its highest point for something that's traveling straight up and down, and the acceleration is not. So the acceleration still points down even when your object is at its highest point. So notice as the object travels up and then falls back down, when it's at the same height, it has the same speed. Whether that velocity points up or down is depending on whether it's coming up or down, and so the y component has a different sign depending on whether your object is traveling up or down. Well, what if I throw it horizontally? So again, still start from the top of the building, but now instead of just dropping it, let's say I throw it horizontally. So now I know I've got some horizontal motion, and the acceleration vector I know points down. Well, the horizontal motion isn't going to change. We've said the whole idea behind the x component of the acceleration being zero is that the horizontal motion is constant velocity motion. So the x component of my velocity vector always stays the same. The y component acts exactly like it did when I dropped the object. So again, it's going to increase as the object falls. And so what you see is at each subsequent point, the x component remains the same, the y component increases. Basically, that dictates what path the ball travels along. So that what we have is a combination of motion with constant velocity in the horizontal and with constant acceleration in the vertical. The object's speed is going to increase as it falls, which again tells me that the y components of the velocity and acceleration point in the same direction on the way down. If I want to figure out what that speed is, I get to Pythagorize. So here I have two non-zero components. So to figure out what the magnitude of the velocity vector is, I'm going to take the x component squared plus the y component squared, take the square root. That'll tell me what the speed is. And the x component doesn't change. The y component gets bigger as the object falls downwards. I can also calculate out the angle that that velocity vector makes with the horizontal, and that angle is going to increase as the object falls. And so again, that's just using the inverse tangent. So I can calculate out an angle that I've labeled theta here relative to the horizontal axis that's just going to be given by the inverse tangent of my y component over the x component. The x component stays the same, the y component gets bigger as my object falls, that makes theta bigger. So let's throw something from the ground now, but instead of throwing it straight up, let's throw it out at some angle. And so again, what's going to happen is it's got two components, x component, y component. That x component isn't going to change, but the y component will. So the vertical component, again, because the acceleration points down, the y component, as my object travels up, it's going to decrease. And so it decreases up until it reaches its highest point. At the highest point, the y component of the velocity vector of my projectile is zero, but the x component is still exactly what it was when the projectile was launched. On its way up, the y components of the velocity and acceleration point in opposite directions, which means that my object is slowing down. At its highest point, the y component of the velocity vector is zero, but again, the acceleration is not. So the y component of the acceleration still points downward. On its way back down, I see the reverse in terms of what's going on with the motion. The x component stays the same. The y component now increases because on its way back down, the y component of the velocity and the y component of acceleration point in the same direction. The x component is unchanged during its entire flight, and again that simply comes from the fact that there is no x component for the acceleration. The object has the same speed at the same height on its way up and on its way down. We've just changed what the sign is for the y component of the velocity, but since I want that y component squared when I Pythagorize, I end up with the same speed. And so projectile motion fundamentally is it's simply a kinematics problem where we know what the acceleration is. And so the x component of the acceleration being 0 means that if we have horizontal motion, it's going to be constant velocity motion. The y component being plus or minus g means that that is a constant value for the y component of the acceleration. So vertically, my projectile travels with constant acceleration motion.